bright it was to be staring at that.
Is the mic on? Is the mic on? I don't think so. Okay. Green.
Go ahead whenever you're ready.
It's warming up.
Yep. All right. Well, thanks everybody for coming. Today, it's my pleasure to introduce James Anheuser, who I do remember contacting me about 4 years ago. I think just sort of cold call out of the blue and saying,
Literally
"Hey,
phone call."
Yeah, it was a phone call. It's like, can I drive up from Milwaukee to come talk to you about coming to grad school?" So James got his BS in mechanical engineering in 2012. Had a 6-year career in the engineering field, and then decided he wanted to come back to school and get into climate research. So he came over to our department. And so James has been a student here since the fall of 2018 in both SIMS and atmospheric and oceanic sciences. You'll probably, some of you will remember, he got his master's degree a year and a half ago or so now, working with Paul Menzel and Elizabeth Weiss on evaluating fusion products, where you take imager data and sounder data with a larger footprint and try to sort of maximize the information from both of those two worlds. And he's since evolved into looking at the cryosphere, trying to develop better products for understanding how sea ice thickness is changing, and ultimately has goals of using this new daily sea ice product that he's going to talk to you about to understand better the changing Arctic climate. So without further ado, I'll hand it over to James.
Great. Yeah, thanks. Maybe it sounds like the mic might be working now. Is that cool? Yeah. Well, yeah. Tristan nailed it. I'm working on a daily basin-wide sea ice thickness retrieval with the ultimate goal of sort of improving our understanding of the Arctic climate. And I'll show you here why better understanding of sea ice thickness is important to that. And I think it is. So we'll start by looking at what's going on with sea ice today. This is from a couple days ago, but this shows on the left sea ice concentration on November 1st in the white and blue contours, and then the orange line is the median from 1981 to 2010, where the ice edge would be. So actually this is not as apocalyptic as it sometimes looks, but you can see that in any case the extent of the ice is less today than it was in average over from 1980 to 2010 on this date. And then if we look at it on a annual cycle scale, we have the dark gray line is the median again from 1980 to 2010. We have interquartile and interdecile, which is pretty faint here at range. The blue line is this year. We can see that we are outside interdecile range, or decile, I don't know which way that's set, from 1981 to 2010. And then plotted here is the 2012 year, which is notoriously a low sea ice year, is oftentimes given for reference. And we see that we are outside of that statistical range. Not quite as bad as 2012, but still low on the sea ice extent. The Antarctic is a little bit of a different story. The changes there haven't been as serious, or what should I say, poignant maybe, or extreme. But still, there are some regions where there was sea ice in a median from 1980 to 2010, but not today. And it might be more that the sea ice is moving or changing in the Antarctic. And the same plot over here, again, it's not quite as extreme. And it's kind of actually a mystery as to why that is versus the Arctic, but that's not a part of today's talk. We then look at the September ice area from 1980 to today, 1979, I guess, with a trend line plotted. September is chosen because that is the minimum ice area month in the Arctic. And in 79, we had almost 8 million square kilometers of ice area in September. And you can see recent years are below 5, approaching 4 million square kilometers, which is a little more than half. Yeah, not great. So we want to know more why that is, but we also want to be able to project forward. But the future projections are fairly uncertain. The top plot is March sea ice area from today through this century. The bottom is September. March is the maximum yearly area, September, again, the minimum. This is from the CMIP 6 model collection under the SSP 8.5 pathway. The light gray are individual models submitted to the collection, and the blue is the model mean. The March picture is a little bit more certain. We can see some agreement, especially into the latter part of this century, then some divergence, but the September area is very uncertain. We can even see that some models are saying that today we have very low ice below this dotted line, which signifies ice-free, which of course is not true. And then we have a whole range of models here that are reducing the area at different rates. A lot of uncertainty. So why so much uncertainty? And maybe I shouldn't have said why so much uncertainty, but why the uncertainty? How can we address the uncertainty and reduce it, whether there's so much or not so much? How can we reduce it? And I've taken this quote from Francois Massenet, I believe is how he said, in 2018. He said, the current main, he didn't say, he wrote, the current main obstacle to reducing uncertainties in projected sea ice volume or area trends is not the complexity of the models used, or rather the lack of long-term and reliable estimates of sea ice volume, not added from thickness, that can be used to constrain their projections. So, while improvements to the models would be great, a more pressing need is actually a climatology with which to compare these models to. And that would come from thickness, sea ice thickness products that then would be multiplied times area to get to volume. We all know geometry. Okay, so that brings us to what I'll be talking about today. I'll start with showing the state of the art for sea ice thickness estimates, climatologies out there today. Introduce my product, which I'm tentatively calling SLICE, Stefan's Law Integrated Conducted Energy. And it's really, the novel part of it is that I'm combining two things that are not novel, which is Stefan's Law for thermodynamic sea ice growth and a snow ice interface temperature retrieval. Show some results and then a summary and next steps. So here is the state of the art of sea ice thickness satellite retrievals with which we build climatologies from. This is from a paper by Xuanji Wang in our building. We have APPX, which is sort of a model applied to a number of observational products. ISAT and CryoSat, which are active altimeters, satellite-based altimeters. IceBridge, which is an aircraft campaign that really is more selective in its time coverage. And SMOS, which is not intended for sea ice thickness measurements, but it's been found to be able to do so on low thickness areas. And PIOMAS, I've added this because it's not part of this paper because it's really a model assimilation more than anything, but it's oftentimes used in the same capacity. And I'll point to a couple of things that really stand out here. So daily coverage for full Arctic, days for full Arctic coverage. With the APPX product, it's daily, but with ISAT and CryoSat, it's nowhere near daily. It actually takes 91 days for the ISAT to cover the whole Arctic because it's sending down a single beam of active information and then receiving the return beam to judge the elevation of the surface. And in so doing, it only can cover a small area below its orbit. So it takes 91 days to cover the entire Arctic. CryoSat takes 28 days, a little bit better, but still a month. Many things can happen to the sea ice thickness in a month. IceBridge doesn't cover the full Arctic. That's, like as I said, it's an aircraft campaign. It's very selective on when it's available. SMOS is daily. So we'd like to improve on the coverage here. We have resolution when it's available. They're all measuring different actual aspects of the the Earth. I mean, we have APBX, which is a conglomeration of many observations, the altimeters, which are measuring surface elevation, and SMOS, which is measuring the brightness temperature. Not quite ideal. We really want to be able to measure sea ice thickness. And we have some accuracy and uncertainty numbers that are really best case values down there, between 0.1 and 0.2 meters. Uncertainties all around half a meter, except for SMOS, but again, only available for 0 to 0.5 meter thick ice. Now I've added up here, this is AVI CS2 SMOS, which is the Alfred Wegener Institute's combined Krausat-2 and SMOS product, which I'll use later in the talk. That's why I'm pointing this out. They were able to take advantage of the daily coverage of SMOS, albeit only in the 0 to 0.5 meter ranges, and combine it with Krausat data available every 28 days to make more of a consistent product. And I point that out just because, like I said, I'll use that later in the talk. Okay, so that's the state of the art. Now I'm going to introduce SLICE, Stefan's Law Integrated Conductive Energy. And we'll start with a sort of governing equation to guide where we go with this. We have the change in thickness per unit time is equal to some function for growth. That's a function of time, thickness, and position x, and minus or augmented by the divergence of the velocity, the drift flow field, and the thickness. And this is similar to an equation from a Thorndike 1975 paper, which is a very important, crucial sea ice modeling paper that really is still the structural, forms the structural part of sea ice models today. So I just note that to say it's sort of based in that infrastructure, so to speak. And then what we can do is divide those two terms. The left is a thermodynamic term because it's telling us how the ice is growing through phase change. On the right, that's more dynamics, where the ice is changing in thickness due to the relative motion of parcels with one another. And that can be thought of as sort of a compressible advection term, where the flow field U is not necessarily continuous because the ice is combining I'm sorry, it's continuous, but it is divergent because the ice is combining, diverging. So it can be thought of as sort of a compressible advection term. But we're going to forget that term for now, come back to it later, but for now we're going to leave it out. And that's because I'm going to introduce Stefan's law of sea ice thermodynamic growth next. And this was first written about in 1891 by, I think, Johannes Stefan. Could be wrong about that. Also written about by Leporanta in 1993. It's called a law because it's very, I guess, influential going forward. It's a part of climate or sea ice models today, much like the Thorndike equation. And I can introduce it by starting with a one-dimensional ice growth model where we have air on top of snow, shows up as the same color here, on top of sea ice, on top of liquid ocean. And what's happening is, in the idealized case, the sea ice is growing downward into the ocean as the liquid water nearest to the ice changes phase. Pretty straightforward. As it changes phase, it releases latent heat. Okay, we all know that's how it works. We've taken chemistry. And then the latent heat, in Stefan's law, is conducted up through the ice to the sea ice surface and eventually out into the atmosphere. So, in Stefan's law, we put an energy balance here between the ice growth phase change aspect of the model and the conduction aspect of the model. And we say that the latent heat of fusion here, as the ice is growing, latent heat is being released, it equals the conduction upward. I've added a temperature plot to sort of show what's happening. The water here nearest to the ice is well mixed and very near the freezing point. And as you go up through the ice, there's a temperature differential, which is driving heat exchange up through the ice, snow, and air. And then we can put symbols to this, make it an actual mathematical relationship where we have latent heat on the left equal to conduction, where we have the change in thickness multiplied by latent heat and the density of ice equals conduction through the ice, defined by the temperature difference on either side of the ice, meaning the freezing point, T sub F, and the temperature at the snow-ice interface, T sub Si, times some conductivity, kappa sub I, and divided by the thickness. This equation on the right is a standard conduction equation. It's part of heat exchange classes you take in engineering. It's very standard. So we have two very standard concepts, latent heat and conduction. We set them equal to each other, and in so doing, we've related the change in thickness, dH dt, to a temperature difference. Pretty nice. There are some assumptions that are inherent here. We're neglecting horizontal conduction. We're assuming no thermal inertia in the ice, which basically means steady state. We assume no internal heat sources. An obvious exception would be shortwave radiation, but fortunately during the ice growth season at both poles, it's polar winter. We don't have much sunlight. There might be some exceptions on the shoulder seasons, but we're neglecting those for now. We're also neglecting heat flux from the seawater. These are reasonable. The last two are a little bit more contentious, I would say. But for now, I'm just going to say these are reasonable, and we can investigate them later if need be. Okay, so then we can solve Stefan's law. Start with our governing equation, rearrange Stefan's law to look a little bit more like a governing equation, and then come up with a solution here, the second to the last line, where we have h, the new thickness, is equal, the square of the new thickness is equal to the initial thickness squared plus a constant squared times s. So a is all of our constants wrapped up into one, and s is what we would call freezing days, which is not important necessarily. It's the integration of how much time the ice, base of the ice, spends below freezing. So the time times the temperature, and everything in these two equations, except for TSI, can be an assumed constant. We have some initial state, we have A, where we have conductivity, density, latent heat. Those all can be assigned values. And we have freezing point here, which we can also assign a value to. So we're pretty close to being able to solve this for a new thickness H, but don't have snow-ice interface temperature. People have done this before solved this before, used this before to find sea ice thickness by assuming that maybe the skin temperature or the temperature at the top of the snow equals snow-ice interface temperature. Or maybe the air temperature at the 2 meter level is equal to the snow-ice interface temperature. All of these methods have been lacking, haven't ended in very great results. But recently, and this is where this work is sort of new, there's been a snow ice interface temperature retrieval developed. It's developed by Sang-Woo Lee and Vijay Son in Korea in 2015. Okay, interesting. A little remote sensing background here. We're going to use the Anheuser E and Anheuser 2 instruments, both passive microwave instruments. We're going to use the 6.9 gigahertz channels from those instruments, which we're going to say are not significantly absorbed by snow or atmosphere. Sort of an assumption there. We're also going to leave out cosmic radiation. And in so doing, we have a couple of radiative balance equations. Look pretty simple. We have the brightness temperatures as measured by the instrument in both the horizontal and vertical polarizations at 6.9 gigahertz. They're equal to the emissivities in the horizontal and vertical polarizations times the snow ice interface temperature. So we're assuming that the weighting function for these channels peaks at the snow ice interface. But what is the emissivity of the ice? Okay, tough question, good question. In the past, people have used infrared data to try to come up with an emissivity, but that's clear sky only. We can use models, but that's a little bit error prone. So we're left with these two equations and three unknowns. And that's where the combined Fresnel relation comes into play. Also worked by Vijay Son and Sang-Woo Lee. We have on the top line, standard Fresnel relations from radiation fundamentals. And we combine them, they combine them via the common adjusted real refractive index N sub R to where one can be defined by the other. In this case, we have vertical polarization, reflectivity, defined by horizontal polarization, reflectivity. And that allows us to close the system. We have the top left, same radiative balance equations, horizontal and vertical, brightness temperatures equal to the emissivities, those polarizations, times the snow ice interface temperature. We have the combined Fresnel relation here at the bottom, and then a sort of statement of conservation of energy where emissivity plus reflectivity equals 1, assuming that the ice is opaque. Now we have 5 equations, 5 unknowns. Solve for TSI. Does it work? Short answer, pretty well. From the Son and Lee paper, there's some validation results. I'll just point to the bottom left plot here. When comparing the retrieval against buoy measurements, they found buoy measurements of snow ice interface temperature. They found a bias of 0.8 Kelvin and an RMS root mean squared error of 0.994. And this here is an example from our paper on January 1st, 2013, showing that this can be solved on a basin-wide scale. A couple of characteristics of this retrieval. We have daily coverage in the polar regions. The Anheuser instruments cover the poles every day, at least once, so that's good. Basin-wide, daily coverage basin-wide, as I said, is covering the polar regions daily. It's only viable over 95% or higher sea ice concentration at this point. There's some ideas for how to get over that constraint, but for now, open water of greater than 5% disrupts the retrieval. We have applied a bias correction of 5 Kelvin. It was found, I found that was needed to bring the results closer to the actual buoy temperatures and improve the final retrieval results. I have some thoughts of why that is. Maybe the snow and atmosphere absorption, neglecting assumption was bad. Not sure yet. can also be adapted to SSMI data beginning in 1987. That's interesting. That would be some pretty nice coverage. So the novel part of the work is to couple that retrieval back to Stefan's law solution. I pulled the solution back up onto the screen, and as before, this TSI was our major unknown here. So in this work, we're plugging in the retrieval into that TSI in the Stefan's law solution. To kind of reorient ourselves about how this would work, we start with an initial ice thickness condition. In order to get the new thickness, we have to have the previous thickness. That's a little bit different than other retrievals out there, and certainly a caveat that I'll get to here. We retrieve snow ice interface temperature from the passive microwave data, and we couple that passive microwave data into Stefan's law to calculate the new ice thickness. This can be applied one-dimensionally, on a basin-wide scale, flexible in that way. It retrieves thermodynamic growth, the top line, and thermodynamic growth only for now. Daily basin-wide coverage, we're talking about slice here now, the combination. It's viable from 1987 to current using SSMI data. It's also self-correcting, which is interesting. By nature of the H-term thickness on the bottom of this DH/dt Stefan's law relationship, thicker ice will grow slower than thinner ice, and vice versa. So if you're thicker than if the product is saying the ice is thicker than it actually is, then it'll grow slower and approach the correct value. We'll never get there, but it'll at least approach the correct value. Caveats, again, it requires an initial condition to retrieve absolute thickness. I think this might be unique. I'm trying to think of other retrievals that might sort of be of a similar mold to look at how certain things like uncertainty are quantified. So I'm thinking about that question and open to thoughts from anybody on how this might be similar to what might be out there. No melt. So row season only. That's all right. Some of the altimeters are also row season only. And it's 95% ice concentration or higher only at this time. Okay. That felt like a lot. Well, let's get to results. How does this thing work? So we'll start with one-dimensional. One-dimensional results for this, we've compared with ICMS balance buoys from CREL, U.S. Army Cold Regions Research and Engineering Lab. They've got these buoys that they put into the ice, they freeze them into the ice. There are acoustic rangefinders above and below the ice that are able to find the distance between the rangefinder and the ice on each side, and in so doing, get the actual thickness of the ice. They're Lagrangian in that they move with the ice pack, which is a good match for validating this retrieval because it's tracing thickness, it's taking along its thickness, and remember we need an initial condition. I've used all buoys from 2003 to 2016, except the one or two that had landfast ice or obvious dynamic effects, because the diameter of the observation of these rangefinders is not that large. It's rare that they actually experience dynamic effects, so it's really just experiencing thermodynamic growth. Again, making it a good candidate for validation here. Taking the initial condition and end dates from the buoy thickness themselves. Use the Anheuser data from the buoy location. And done this all on a daily mean. Okay. And here are the results with sort of small font. Apologize for that, but we have 10 buoys. The blue lines are the buoy thickness measurements. For each of these is a season, so fall through spring. The blue is the buoy measurement, and the red is the slice thickness measurements. Again, we've taken the initial condition from the buoy, so you'll see that all of these red profiles start at the buoy profile. So, you know, something to consider here. It starts with the buoy thickness, but then from there, it follows the buoy thickness very, very well. Where the bias is 8 millimeters with a 0.059 meter or 60 millimeter standard deviation. And the linear correlation values end up averaging to 0.991 with a standard deviation of 0.01. So with an initial condition from the buoy, I'll make that clear, and then applying slice to the thermodynamic growth from that point, the results are very good. Okay, what about basin-wide? So that we can do this basin-wide, what does it look like? So for this, we've used as reference data sets that UW-CS2 SMOS product that I explained earlier, and PIOMAS, which is the model assimilation product that I showed on the right. So we have an observation product and sort of a model product that we've used here. I've taken the initial condition from those data sets. One set uses one, the other set of plots I'll show uses the other. Taking basin-wide initial conditions. So taking the entire basin's thickness from those products as the initial condition. I've applied slice daily to the whole basin. And as the ice grows horizontally, new ice parcels are initialized at 0.05 meters. So if there's a grid cell where a CS concentration product says, oh, we have ice here now, it's initialized in slice at 0.05 meters, which is, there's some basis in literature for that, which I don't cite, but. And this is all on a 25-kilometer east grid 2.0, equal area scalable something grid, 25-kilometer scale. First, as an example, I'll show the 2012 to 2013 year, where November 2nd, should be first, shows the initialized thickness from, this one is the UW-CS2 SMOS. Applied slice basin-wide, daily. Here I'm plotting monthly. We can see that the thickness increases and the area increases. The thickness is increasing, again, thermodynamically only, and there are no dynamic effects. Kind of hard to see with this particular color scale, but the structure of the thickness is staying consistent from month to month. It's really just getting thicker. We're not rearranging the ice from day to day as would happen in the actual system. But the thickness is growing. Okay, well, what is the adverse effects of not having those dynamics? Here we have 2013 through 2020, the end of each of these growth seasons, from slice and in the first column, fourth column, and AVI next to it. And then the differences. And the differences here is where we see what are the adverse effects of not including dynamics. For the most part, the differences are between -1 and 1 meter, which is not bad. But most interestingly is the differences reflect expected dynamic effects. Many of these look the same, where in the areas where climatology of Beaufort gyre, of transpolar drift, tend to increase sea ice thickness, such as north of the Canadian archipelago, getting into the Ferrand Strait, the slice retrieval underestimates sea ice thickness. It's not accounting for the movement of the ice in those regions. And then in the marginal seas north of Siberia, where the ice is usually moving from, the product overestimates sea ice thickness. So that's interesting. It means, you can kind of take that to mean that the slice product is reflecting thermodynamics well, and as expected, not addressing the dynamics. And again, this similar story from year to year. This is the same exact thing, but with PIOMAS. PIOMAS is a set of models, so the results are a little bit more smooth. But again, we see, underestimated ice here, where the movement of the ice would increase the ice thickness, and an underestimation in the areas where that ice would come from. And that's reflected in many of these. And then, what does this mean for the volume, the overall volume, total volume, not just the arrangement of the thickness in the basin, but the total volume of the ice in the basin. So for that, I've integrated across the basin for both top chart is CS2, SMOS, bottom is PIOMAS, integrated the thickness change from the beginning of the season to the end of the season across the basin. And we've got the slice growth beginning to end of the season for each year, CS2, SMOS growth, the difference, and then the relative difference between slice and CS2 SMOS. And the CS2 SMOS slice, right, overestimates thickness volume change relative to CS2 SMOS and underestimates volume change relative to PIOMAS. That's kind of encouraging to see that, okay, we're falling within the range of two existing products for total volumetric growth. And this is because the dynamic effects don't directly add volume. If you remember back to the governing equation, it's a divergence of the flow field times the thickness. It's not directly changing the volume, it's just rearranging it. There are some downstream secondary effects, but not including the dynamics, as expected, does not necessarily throw off the total volume growth across the basin, which is also encouraging. Okay, so in summary, make a good time here. Slice couple Stefan's law with a snow ice interface temperature retrieval. That's what it does, that's what's new about it, that's how it works. It captures daily basin-wide thermodynamic sea ice growth very well. The differences with reference data sets reflect expected dynamic effects, and the volumetric growth falls within reference data sets that are accepted parts of the science. There are some assumptions listed out here, worth investigating. It's only valid at this time for 95% sea ice concentration, likely leaving out the marginal ice zones. I treated the constants, freezing point, ice density, ice conductivity, as constants. I didn't put them in here, that might have been worth it, but they're not listed in here. But I did treat them as constants, which of course is not reality. So maybe changing those with location in the Arctic Basin might help. Let's return to the motivation here, where we want a long-term and reliable estimate of sea ice volume from thickness. We're kind of getting there. We had the volume aspect that I showed, but we're still lacking the dynamic effects that are important. So next steps here, I've removed the big red X in front of dynamics because I would like to include dynamics in this was all kind of chapter 1 of my thesis. Chapter 2, I'd like to include dynamics by using an ice motion observational data set. This one is from the Mark Chudy product. It's well accepted and used, where there are weekly, he also has a daily data set of ice drift going back to 1978. If I can include that as the flow field vector, U, in that divergence sort of infection term, might be able to improve the results and include, and not have those dynamically driven differences with other data sets. And if that works, I'd like to create a climatology from 1987, which is when the snow ice interface temperature data is available. In order to understand how dynamics and thermodynamics have changed relative to one another, where in the regions, what regions have changed in what direction, just how dynamics and thermodynamics have changed since 1987. There's a lot of question in literature about, is the ice moving more? Is the ice moving to different areas? And what is that doing for the overall ice pack from a climate perspective? And I'd like to have that be chapter 3, if chapter 2 works. And I would call it slice plus dynamics. Kind of childish, but I like it. Next steps also, this might have a chance to be sort of an operational product, and that would require a little bit more technical work on the retrieval side as far as constants, assumptions, uncertainty quantification, all that kind of stuff. If anybody's ever read a algorithm theoretical basis document, ATBD, there's a lot of real technical work that is needed to get something to the operational phase. I don't think that would fit necessarily within my dissertation, but something that could be done. Comparing this to global climate models, I mean, the whole motivation really was to do this. So I'll probably have a little bit of that in my second chapter, but that's worth doing. And any number of other intriguing science questions I think would be worth investigating with this product. And I think that's the end. So thanks for being here. Thanks for listening. I appreciate it. Anybody have any questions? Yeah, Ian.
So you did this only for the bird season, but you were trying to implement this for everything else. Are there ways that reworking the slice algorithm for dot bombs and stuff like that?
Yeah, well,
Can you repeat the question?
oh yeah, sure. He asked if this could be adapted to the melt season, which is a good question. The thermodynamics of the melt season are different within the actual ice layer, as you can imagine. So it would take some kind of different mathematical arrangement. In fact, the IceSat, CryoSat-2, probably even SMOS are off during the melt season because the presence of water on top of the ice really just throws off the rate of transfer immensely. So probably it would be difficult, but that would be great. And then I wouldn't need an initial condition for every year. So maybe, but that's a little tougher of a question. Yes?
Do you have any sense on how much the dynamics are important at different times in the growth season?
Ooh, I don't have a sense for that. That's a good question. As you can imagine, there probably is some kind of annual cycle of climatology to how weather is moving the ice. And you would probably know more about that than I don't know. The question of how dynamics is changing over time and varies from region to region is still very much an open question. And what's it going to do under a changing climate? Also an open question. So I don't.
Kind of coupled with that,
Yeah.
have you looked at different teleconnections and whether or not this slice works better and like positive or negative NAO?
Nope. I have not. All good questions. And that's the kind of thing that I think this could be used for in the future, is if I truly am able to get a higher spatial and temporal resolution of thickness, changing thickness, movements of the ice pack. Those types of questions will come into play for sure. Probably outside of my expertise, but I think we could be used to that for sure. Rudy.
Yeah, nice talk, James. Can you move back to the assumptions of your model?
Yep.
Okay, thanks.
Let's just go to the one on the summary slide. Can you read that?
Yeah.
Okay.
Yeah. So in the last point, you say no heat flux from the seawater.
Yeah.
So does that mean that the ocean warming and the dynamics between like the ice and ocean interactions, you are neglecting that portion in your model, or are you?
Well, the question was if I'm neglecting changes to the temperatures at the surface of the ocean. And I guess, you know, I neglect any heat transfer from the ocean to the ice, for sure, on a time-step by time-step basis. But because this is sort of observationally based, if the ocean surface temperatures are changing over time, that's going to affect when the ice starts to grow. So, you know, based on using sea ice concentration products alongside this, if there's no sea ice, then I'm not going to show sea ice in my product. So if the ocean is warmer and not allowing sea ice growth, then there might not be ice. And, you know, once the ice starts growing, the first, I don't know how much depth, but some amount of depth is at the freezing point. It's mixed and at the freezing point. Once that starts, it stays that way until the ice is done growing. As far as I know, it's a little outside of my expertise. And you know, it is kind of a bad assumption. I mean, there is some heat flux from the ocean to the ice. It's not easily quantified, not well understood.
Yeah. Isn't that heat flux from the ocean to the ice is your ice broke?
Just what?
That's your ice broke, right? The heat flux from the ocean to the ice is your ice broke.
Well, yeah, okay. Yes, through the latent heat.
Yeah.
But there's also a component of just heat transfer from the liquid water to the frozen water. There's like less than 10 watts per meter squared of heat that just, aside from the latent heat, is transferring from the ocean to the sea ice. So in actuality, you know, this will be a little bit tilted, and not only will there be latent heat over here, but there will be some heat flux term that's just moving through the system from the bottom to the top. And in the results we see here, kind of throwing it off. Does that make sense?
Yeah, is that like a radiation then?
No, it's like it would be in heat transfer engineering term, we call that convection. It's just water, liquid water, transferring its internal energy, its enthalpy, its heat to the solid ice.
Okay.
Through
like turbulent.
Sure, yeah.
Generation.
Like you can imagine probably the northern Atlantic, it would be higher,
Oh, got it.
if not very high. I don't know. Yeah, Brad.
I guess it's kind of along the same question, because what if there's no snow, and then, I mean, in some sense, the snow is decoupling the ice from the atmosphere. But
Yep.
if there's no snow, then could there be radiative fluxes that you're not accounting for? I don't, like sublimation, which I'm sure is very small, but
Yeah.
are those terms actually significant?
So those terms are wrapped up in snow ice interface temperature. So you can imagine if this is our temperature here, yeah, maybe there are, well, there definitely are. There's radiation, long wave radiation emission coming off of the sea ice surface. Surely there are processes in the air that are pulling.
Okay, it's because you retrieve it.
Yep.
You're constraining that.
Correct. It's the system is only the ice,
Okay.
and the temperature. Yeah, you got it. The snow ice interface temperature reflects all of those.
Okay.
Yep. Which is kind of why this is kind of interesting that you can sort of close it off. Yeah, please.
So this would be super cool if you can go all the way back to 1987. I don't have an encyclopedic memory for PIOMAS or other products that are using different conditions. Did those go back to 1987? If not, what are you going to use it for?
Yeah, this is why I lay awake at night. PIOMAS goes back to 1978, so the short answer is I can use PIOMAS. But, you know, then the question is like, how different is this going to be than PIOMAS? What does it add that PIOMAS doesn't? Yeah, I mean, there are some intricacies to PIOMAS and its availability and all that. But at the very least, it'd be another addition to the dataset library, I suppose. Yeah, Tristan.
Yeah, just all this conversation about the terms that are, being neglected and how important they are. Does that have any connection at all to this 5 Kelvin brightness temperature correction that you mentioned?
Yep.
Okay.
Definitely. I mean, in fact, in the paper I write that, this mystery, I don't know, forget the slide, this mystery 5 Kelvin that I had to apply to get it to match better, it probably accounts for the extent to which assuming no absorption by snow and atmosphere is wrong. I've actually even found other studies that peg that at about 5 degrees Kelvin. But of course, that's not going to be a constant value. It's just that 5 Kelvin seems to be the best here. Yeah, surely snow depth, clouds, all those things would affect to some extent. Yeah, but I don't know those extents yet, and it kind of works as it is, but for sure that'd be an area worth investigation. Yeah, Vision.
I think, thanks for the talk. I was wondering if there is a particular reason for assuming that like the steady state assumption that you have for the model, like that is valid over daily time scale? Is there like a particular
Yeah.
peak capacity thing or something?
Yeah, the reason for assuming that it's steady state is that allows this flux. So imagine this is just Q flux equals this term. Assuming it's a steady state allows the heat transfer to be defined by 2 temperatures. So if there was some thermal inertia, this line would not be straight. And in actuality, there is some amount of thermal inertia, where this line would be curved in some way. And rather than being able to solve it for the Q across the sea ice as constant, it would be specific to the elevation and be more discrete, and it would just be more complicated. But this assumption of no thermal inertia is typically used for stuff like this. But yeah, sure. I mean, especially if there's like a quick change to the weather conditions or to the temperature there will be some thermal inertia for sure. In fact, one of the ideas I had with this product is trying to actually quantify how much there is by comparing the slice results to a buoy and then using some sort of heat diffusion model to actually try to model. I actually have done a little bit of this, seeing if I can model that inertia using a heat diffusion equation. But yeah.
Sorry if I missed this. How have you accounted for uncertainty in the initial ice jump?
I actually hit a slide on that because I didn't think I had time. So I haven't, but because of the H term here, remember I mentioned how it kind of like self-corrects. So I've taken initial conditions and displaced them by a quarter of a meter on either side. And I have a plot that shows like how they diverge. Let me show you after, I guess. But I guess so what I kind of say is, the paper is, it's as good as the initial condition, more or less. And it's heavily reliant on initial condition, for sure. That's why I kind of focused on volumetric growth, not absolute volume, and why I'm also focusing on thermodynamic and dynamic growth and their interplay over the years, not absolute thickness. I think it's maybe not quite as well suited for that kind of thing based on, you know, the uncertainty there related to